Hi everybody, this is your AP Biology teacher. We're going to go over some chemical review. This is stuff you should have learned in chemistry, but we're just going to review it so that we're all on the same page as we jump into biology. The two learning objectives for this video are that matter consists of chemical elements in pure form and in combinations, which we call compounds. And I'm going to give you some other vocabulary words that go along with it, as well as we're going to look at the structure of the atom and look at how the structure of the atom determines chemical bonding. So that'll happen kind of in two videos, but let's just jump right in. So to start with, we've got some vocab terms, okay? The first thing I want to talk about is what is matter? So let's talk about what is matter. So matter is anything that takes up space and has mass. So it has volume and it has mass. So anything in our universe that basically is physical, it could also be air, it could be, anything that you can see is made up of matter. And matter by itself is made up of atoms. Now, atoms, if you remember, are the smallest unit of an element. Let me finish writing this. Unit of an element that has its chemical and physical properties. Okay, so for example, if I'm looking at, let me get a different color. If I'm looking at an atom of gold, so gold's chemical symbol is Au. The single atom of gold has certain chemical and physical properties. And if I start talking about the atom of gold, that is the smallest piece of gold that still holds those properties. I can't go smaller than that. Once I go into subatomic particles, which we will talk about, you lose the chemical and physical properties of that element. So let's go on a little bit further. We're going to talk about how we put these things together. So I can put two atoms together. So let's say I'm talking about oxygen. I'm going to put two oxygens together. So here's one oxygen and it's bonded together, right? So I have O2. This is what we call a molecule. Now this can also be called a compound, all right? So what is the difference between the two? A molecule and a compound both are, they both have to have more than one atom chemically, and that's key, chemically combined, chemically put together. It has to be chemically. The difference is a compound has to be two different elements, okay? Whereas a molecule can be two different, but it can also be two of the same. So it can be same or different. So for example, my oxygen here, that is a compound. But if I'm looking at C6H12, H12O6, which is sugar or glucose, that is a compound, not a molecule. So hopefully you understand the difference between those two. Now, how does that differ from a mixture? Well, a mixture is when I have a bunch of molecules, compounds, atoms, whatever you want to talk about, mixed together, but not chemically mixed together. So for example, when I dissolve salt into water, right? So those are dissolved together. I can physically separate the salt out of the water. So I'm not changing the water, really. The water is still H2O and the NaCl is still NaCl. I'm not creating new compounds. And I can separate them physically. All I have to do actually is boil the water. If I boil the water off, I'm left with salt. So that's what a mixture is. So those are some vocab words that are really important that you understand. So now let's talk about what elements make up life. And we're going to talk specifically about human bodies because, well, that's what we are. We're humans. So the four that I really want you to know are C, H, O, and N. CHON. Okay, so carbon, hydrogen, oxygen, and nitrogen. If you add that up, what does that come to? It's over 90%. And surprisingly, some of you might be surprised to learn that oxygen by mass is 65% of our body. Now, understand that oxygen is found in a lot of compounds in our body. For example, water, H2O. And we're talking about by mass. So of these, oxygen is probably one of the heavier elements of those four. Now, we do also have a bunch of others that are what we call essential elements. So we cannot live without these elements. Potassium, sulfur, phosphorus, sodium, all of those are super important. And you're going to find out why. Like as we talk about things like Muscle contraction, you have to have potassium for that. It's absolutely required. Neurons require potassium, sodium, and chlorine. So ions in your body are going to be really important. So those are what we call essential. Then we have something called trace elements. Now these are also really important for life, but they're found less than 1% of your body. So for a long time, we didn't actually know that we needed these. And these are kind of surprising. Who knew that we needed copper, right? Who knew that we needed iodine? A lot of these you're going to find when we get into enzymes. A lot of these are cofactors that help enzymes work really well. So we'll talk a little bit more about those, but it's important that you know the 4 CHON. It's important that you know the definition of an essential element and that you know what a trace element is. All right, so moving on. So let's talk about the structure of an atom. And I know you guys have seen these drawings before. You have a nucleus, which is found in the center of the atom. And inside the nucleus, you have protons and you have neutrons. And this is where all of the mass of that atom is found. Electrons have what we call a relative mass of 0. Obviously, they're not exactly 0, but they're so small. It would be like if you got on a scale and weighed yourself, and then you put a ring on. The ring does have mass, but the amount of mass it has compared to your overall mass is insignificant. And so that's kind of what we look at. So when you look at atomic mass, that comes from the nucleus of the atom. And so when we look at what the atomic mass is, that is protons plus neutrons, and it's all in the nucleus. Outside of the nucleus is a bunch of empty space. It is surprising how much of us and the world is made up of empty space. And in that empty space are electrons. And remember that electrons are negative. They have a negative charge. Protons have a positive charge. And then neutrons are neutral, so they have no charge. Okay, so the electrons are going to be super important when it comes to bonding and all kinds of chemical properties, but electrons are negative in their charge, and they're found in what we call energy shells outside of the nucleus. Now, I want you to understand just how much empty space we're talking about. If you've ever been to a huge football stadium, I'm going to try and draw a stadium here, right? So here's the football stadium, here's the football field, here's 50-yard line. And this is, I'm talking professional football, so huge, like 75,000 people at a stadium. In the center on the 50-yard line would be a marble. That's your nucleus, okay? Now zipping around the stands, and a picture in a ball, like it would be round, it wouldn't be the shape of a stadium, but I wanted you to get this idea. Zipping around the stands are the electrons. Everything else, empty space. That just blows me away. I think that is absolutely crazy. The reason we don't fall through the empty space, like why I can't push my hand through a desk, is because the electrons are all negative, and so they repel each other. And so we'll actually have a discussion about, do you actually touch anything? It's kind of cool. So anyways, that's the basic shape of an atom. Now let's talk about how to read the periodic table, because that's going to be important also. Obviously, this is boron. B is the symbol. The name is shown there. Remember that a lot of times, or sometimes, the symbol doesn't match the name. So for example, potassium is K, gold is AU, silver is AG, lead is PB. Some of that comes from where they're found. It comes from Latin names, all different reasons. A really important number is the atomic number. The atomic number tells you a lot of information. This tells you the number of protons. It also tells you the element, and it determines, well, if it's neutral, it tells you the number of electrons. So in its ground state or neutral state, boron has how many protons and how many electrons? It has 5 of each, okay? This number down here is the atomic mass. Now, this also gives you a lot of information. This tells you, like I said before, the number of protons plus the number of neutrons added together. So if I know that there's 5 protons, all I have to do is subtract it from the mass to get the number of neutrons. Now, obviously, I can't have a partial amount, so you need to round. So if I round this up to 11, subtract 5 protons, that means I have 5 neutrons, okay? And you will need to be able to do that. So a question I might ask would be, I give you this picture and I say, okay, how many protons, neutrons, and electrons are found in boron? 5 protons, 5 electrons, and 6 neutrons. Now, the couple things I want to talk about real quick is valence electrons, why those are important, and then last but not least, what happens when you change each number of these. So let's start with valence electrons. Valence electrons are found in the outermost shell of the atom. So if you remember, I talked about how your electrons are found outside of the nucleus. So here's the nucleus, and then you have these energy shells outside. This is where the electrons are found. So the outermost shell is called the valence shell. And on that valence shell, or in that valence shell, are the valence electrons. Now, these are important because the valence electrons are what determine chemical properties. So they determine bonding, they determine reactivity, they determine, is it going to be an ionic bond? Is it going to be a covalent bond? It determines everything about that atom. So valence electrons are really important. Now, there is something called an octet rule. Remember that octet means 8. 8 is octo, okay? It basically states that in the outermost shell, in all shells actually, except for the very first one and the outermost ones, atoms really want to have a full outer shell. And a full outer shell is 8 electrons. And so it is going to bond based on this octet rule. So it can do that in 2 ways, and we're going to talk about this in the next video, but basically it can do it by transferring electrons, which makes ionic bonds, or it can do it by sharing electrons, which is covalent bonding. So basically, remember though, it's doing it to get 8 electrons, except for 2 elements or 3 elements that only want 2, and we'll talk about those, the exceptions. But it wants 8 in order to have a stable outer shell. If it's not stable, it's going to want to bond, and that indicates reactivity. So hopefully that makes sense. We will certainly do some practice with that. Now let's go over ions and isotopes. I want to talk about what happens when you change each one of the subatomic particles. Okay, so here let's talk about sodium. Okay, sodium has 23 protons, 23 electrons, and I believe it also has 23 neutrons. Now, let's talk about what happens if I change each of those numbers. I'm going to start with the protons, okay? If I change the number of protons in this, it doesn't happen, first of all. You cannot change the number of protons. But if I were to do that, I would change the element. Okay, this is what in the real early times they were trying to do with alchemy. They were trying to change, lead into gold by changing the number of protons. You cannot do it. All right. So, and by the way, this symbol delta means change. So if you change the number of protons, you're changing the element. So basically, don't do that. You cannot do that. You'll create a black hole and the world will get sucked into it. Just kidding. All right. If I change the number of electrons, which does happen, happens very often, you create an ion. And an ion is a charged element and a charged atom. Okay. If I gain electrons, I become more negative, right? And we call that an anion. I always call this a negative ion. That's how I remember it. If I lose electrons, I become more positive. And that is called a cation. And I remember that because, well, I like cats and cats are positive. Get it? Paw. Okay, anyways. So what happens if I change the number of neutrons? So I'm going to put this one over here. If I change the number of neutrons, I create something called an isotope. It is still the same element, just like on ions. It's still the same element because we have not changed the number of protons. But understand that if I change the number of neutrons, remember that that is found in the nucleus, right? And therefore, I'm going to change the mass. So an isotope is the same element, but it has a different atomic mass. Now, examples of this would be like carbon-12, carbon-13, carbon-14. We use carbon-12 for dating, not dating like Tinder, but dating like seeing how old like the Shroud of Turin is. We look at radiometric dating. There's a lot of isotopes that are used in medicine, especially for example, in PET scans, PET, positron emission topography. A PET scan looks at how much glucose your brain is using to see what areas of your brain are active. And they use, I want to say they use, I don't know which one they use, but they basically use an isotope that lights up. It tags the glucose and lights up so they can see where that glucose is being used. So that's all I wanted to do on this. Let's just really quickly go back to the learning objectives, make sure we hit them all. You understand that what matter is, you understand a compound versus a molecule and a mixture. You also understand how atoms, like the shape of the atom, and especially the valence electrons, determines the structure and the property of that atom. That's it for this one. Make sure to get your reading guides done, and I'll see everybody in class. Thanks.